Hi, welcome to the different types of induction motor, single phase induction motor, where we require the starting of induction motor is very important. So we make changes in the construction in the stator part where the induction motors are self-starting. So based on the changes what we make in the single phase induction motors, stator part, we classify different types of single phase induction motor. So to begin with, the different types of induction motor, single phase induction motor are split phase induction motor, capacitor start induction motor, capacitor start, capacitor run induction motor, and shaded pole motor. So as we know that for any torque to produce, there should be an interaction of two fluxes. So we do have stator flux already, phi 1. Since the stator flux is alternating in nature, and the torque produced by that resultant torque produced by that alternating flux will be zero. So there should be an additional flux inserted into the stator, so which has a phase difference between alpha from the main flux. This is the additional flux in the stator, that is phi 2, which has a phase difference of alpha. If this alpha increases, the torque can also be increased. So starting torque depends on the value of alpha. So coming to the split phase induction motor, this is the arrangement made for the split phase induction motor. This is the cage rotor, squirrel cage, and this is the main winding, that is the stator winding. So for that, in addition to the stator winding, it carries one more winding which is called auxiliary winding, that is starting winding here, or auxiliary winding, which carries a series resistance such that its impedance is highly resistive in nature. So ensure the starting winding impedance is highly resistive. The main winding is inductive, and this is highly resistive in nature. So that it produces from the supply, when you draw a current, it produces a main current I, which resolves to the IM, that is a current going through the main winding, and we have a current flowing here. So we have provide a centrifugal switch also here. Um, uh, where if you look at it, the main winding, this IM, is inductive, so this lags the supply voltage by an angle phi m. So if you look at this supply voltage V, the inductive in nature, this lags the supply voltage by an angle phi m, because as I said, this is not purely inductive, it has less resistance, so you cannot have a pure inductive in nature with this vector. So there exists a phase difference of alpha, and you have the starting current ist in this winding. As soon as you close the switch, the starting current ist will have also be lagging the supply voltage, because this is also inductive but highly resistive in nature. So this makes angle of alpha with respect to this im. So as I said, there should always be a phase difference alpha between these two currents, so results for flux which has a alpha as a phase difference. So this is shown in this phasor diagram. So the resultant of these two fluxes, which is created by this ist and im, okay, due to this starting torque will be produced, which will be acting in only one direction. So if you observe, the resultant of these two will be the current I, which results in the flux, which will be in rotating and resulting in a starting torque. So this is the graph for the split phase. So this auxiliary winding, to this starting winding is also called as auxiliary winding, has a centrifugal switch in series. So when motor gathers a sufficient speed up to 75 to 80% of synchronous speed, this switch you can remove it, and still the rotor will be running, and though even the auxiliary winding is cut off from the circuit. So the motor runs only with the stator winding once it is accelerated. So the auxiliary winding is designed for a short time, while the main winding is designed for continuous use. As the current IM are splitted from each other by an angle alpha at start, the motor is commonly called split phase induction motor. The torque speed characteristics is as shown here. So the starting torque TST, if you look at this, this is starting torque TST is proportional to the split angle alpha. So if alpha increases, the torque angles also, the torque also increases. So, but split phase motor gives poor starting torque, which is 125 to 150% of full load torque. The direction of rotation of this motor can be reversed by reversing the terminals of each main of auxiliary winding. This changes the direction of rotation, which in turn the direction of the motor. So the applications of this type of split phase induction motor, because they have very low starting current and moderate starting torque, these are used for starting loads like fans, blowers, grinders, centrifugal pumps, washing machine, oil burners, office equipments, etc. They are available basically in the range of 1 by 120 to half kilo watt. So if you look at it, this is a full load torque. So it is the torque achieved by the split phase is just 125 to 150% of the full load torque. Coming to the capacitor start induction motor, if you look at it, depending on whether the capacitor remain in circuit permanently or disconnected, you can have the capacitor start and capacitor run motor. So the construction of this motor is similar to the resistance split phase type. The difference is that in series with this auxiliary winding, we have a capacitor connected. The capacitive, the circuit will draw the leading current. Okay, this feature is used in this type to increase the split phase angle alpha. So if you look at that, the current, instead of lagging, it will be leading here, and the phase angle between Im and Ist is again an alpha, which results in the current I, which causes the forward rotation of the rotor because the torque is produced here. So the capacitive circuit, as it draws the leading current, which is mainly used in this type of split phase angle. Depending on whether capacitor remains in circuit permanently or not, we can classify that is, if it is used only at the starting, we call that as capacitor start motor. If the capacitor is retained even after running condition, it is called capacitor start, capacitor run motors. The connection of this capacitor motor is as shown here, and the phasor diagram here. The current Im lags the voltage by an angle phi m. Okay, and phi m, while due to capacitor current, and Ist will lead the voltage by an angle phi st, and the phase angle difference between Im and Ist is alpha. So this is an ideal case, the phasor diagram as shown here. So the resultant current is produced. So the torque is proportional to alpha here, and hence such motor produce very high starting torque. If there is a leading current, it produces a very high starting current. So when speed approaches to 78-80%, this can be removed by opening the centrifugal switch. So hence it is called capacitor start motor. So in this case of capacitor start motor, there is no centrifugal switch and capacitor remain. In case of capacitor start, capacitor run motor, this centrifugal switch is removed so that this capacitor is there during start and during the run condition as well. So if you look at it, the switch is removed. And if you observe the starting torque, if it is only used, the capacitor is only used during starting, the starting torque is just 150%. If you use the capacitor start, even after running condition, the torque produced is more than 350% of the full load torque. 350 to 400% of the full load torque. So this is the characteristics of torque and speed. The applications of this kind of capacitor start and capacitor start run induction motor, which has a high very starting torque, are used for hard starting loads. These are like compressors, conveyors, grinders, fans, blowers, refrigerators, air conditioners. These are more commonly used motors. And these motors are available up to 6 kilowatts. So the induction motor using capacitor start run motor can be used up to 6 kilowatt. Thank you for watching.